So in this video, I'm going to go through 3 more gas laws. And the first gas law is going to be Charles' law. And so that allows us to relate temperature and volume. Okay, so here's the formula for Charles' law. It's V1 over T1 equals V2 over T2. So if you notice, if your volume increases, what that means is that your temperature is going to also increase so that that proportion doesn't change value. So while for Boyle's law, it was P1 V1, and when pressure increased, volume had to decrease, so they were inversely related. Charles' law shows us that volume and temperature are directly related. So when one goes up, the other goes up. When one goes down, the other goes down. Okay, and so you can see that in this diagram right here. When I'm at 200 Kelvin, if I increase the temperature, notice that the volume of that cylinder, it's a piston, right? Those gas molecules start moving more quickly, and as a result, the volume expands. So that further demonstrates that volume and temperature are directly related. Okay, the units for temperature, so remember for Boyle's law, your units for pressure and your units for volume could be whatever you wanted them to be as long as they matched up on both sides. Whenever we're dealing with temperature for our gas laws, however, temperature must be in Kelvin. Okay? So let's look at an example. So here it tells you a balloon is inflated in a room at 24 degrees Celsius and has a volume of 4 liters. The balloon is then heated to a temperature of 58 degrees Celsius. What is the new volume? So I'm going to be using my Charles' law, V1 over T1 equals V2 over T2. Keep in mind, your temperature must be in Kelvin. So to convert from Celsius to Kelvin, I need to take my Celsius temperature and I need to add 273 to that. Okay, so I'm going to put 4.00 liters on top, 24, which is my T1, plus 273 gives me 297. That equals my V2, which is, I don't know, so I'm going to put V2 right there, over T2. Well, I need to take 58 degrees, and I need to add 273 to that, so you would get 331. Okay? Now I need to cross multiply. So what I'm going to do is I'm going to take my 297, multiply that by V2, and then I'm going to set that equal to 4.00 times 331. Okay, so I've got that there. Now to isolate V2 to get it all by itself, I need to divide both sides by 297. And so the answer that I get for my V2, once I divide by 297, and I round to the correct number of significant figures, which in this case would be 3, because 4.00 has 3 sig figs, 297 has 3, and 331 has 3 significant figures. I get 4.46 liters. The important thing for you to remember, even though the Celsius temperature has 2 significant figures, the important thing for you to remember is since I'm adding 273, I'm going to base my significant figures off of the Kelvin temperature, not the Celsius temperature. Okay? Let's look at another example. Here's Gay-Lussac's law, and this, as you notice, relates pressure and temperature. It looks just like Charles' law, except now I'm looking at pressure instead of volume and that relationship with temperature. Okay, notice again, pressure and temperature, just like for Charles' law, they are directly related. So when pressure goes up, temperature goes up. When pressure goes down, temperature goes down. And that makes sense if you look here. If you take gas, and you have it under, for example, 200 Kelvin at a pressure of 1 atmosphere, if you increase that temperature, those molecules, those gas molecules, are going to start moving much more quickly. And as they're moving more quickly because you've increased the temperature, the force with which they hit the walls of that container, that's going to increase, which is going to increase the pressure. So once again, just like in Charles's law, you need your units of temperature to be in Kelvin. Okay, so let's look at an example. It says a gas system has an initial pressure and temperature of 12 atmospheres and 27.9 degrees Celsius. If the pressure changes to 3.74 atmospheres, what is the resultant temperature? All right, so my pressure is 12 atmospheres. Okay, so I'm going to plug in 12 atmospheres. My temperature is 27.9 degrees Celsius. I've got to add 273 to that to get that into Kelvin. So it's going to be 300.9 Kelvin. That equals 3.74 atmospheres over my T2. Notice my units for pressure can be whatever I want, but they have to be the same on both sides. So in this case, they're both atmospheres. If they were both millimeters of mercury or they were both kilopascals, that would be perfectly fine. I'm going to cross multiply, so I have 12.0 times T2 equals 300.9 times 3.74. I'm going to divide both sides by 12.0 to get my T2, okay? And what I end up getting is 93.8 Kelvin, okay? Now, if I had asked you, what would the temperature be in Celsius? This is a problem that really messes students up because they immediately say, well, if the answer has to be in Celsius, then I can just keep all of my work in Celsius, and that's not the case. You always have to convert to Kelvin, but then at this point, right when I'm done, then in order to get back into Celsius, you would have to subtract by 273 to get your answer. Okay? And that's it. Just always make sure when you're using your gas laws that you're in Kelvin and you're not in Celsius. So if I ask for it in Celsius, then I would subtract 273, okay? And my answer would be negative 179 degrees Celsius, and it would be that because 273 has no decimal places. So I would round this so it has no decimal places, so that makes it negative 179. Your last gas law is the combined gas law, and if you notice, it takes all the gas laws that we looked at and combines them together. Keep in mind, if you notice, you can get every single one of the gas laws we've talked about from the combined gas law. So for example, if your temperature stays constant, meaning you're going to ignore T1 and T2 because it stays the same, you've got Boyle's law, P1V1 equals P2V2, which shows that pressure and volume are inversely related. If instead I kept pressure the same, then I would have Charles's law, V1 over T1 equals V2 over T2, showing that volume and temperature are directly related. And then finally, if my volume stays the same, I've got Gay-Lussac's law, P1 over T1 equals P2 over T2, showing that pressure and temperature are directly related as well. However, if all three of these variables change, then I need to use the combined gas law. So let's look at it. In this problem, it says a child has a toy balloon with a volume of 1.80 liters. The temperature of the balloon when it was filled was 20 degrees Celsius and the pressure was 1 atmosphere. So I've got three variables now. Let's make sure all three of those change. If the child were to let the balloon go and it rose 3 kilometers, extra information that you don't need to know, we don't really need to know how high up it goes, but notice the pressure changes to 0.667, so we know my pressure has changed. The temperature goes from 20 degrees Celsius to negative 10 degrees Celsius. There's my second variable that has changed. What is the new volume? So all three variables are going to change. Therefore, I know I need to use my combined gas law. So I'm going to use P1V1 over T1 equals P2V2 over T2, and I'm going to plug in all the values that I know. So I know my initial pressure is 1 atmosphere. I know my initial volume is 1.80 liters. Okay? I'm going to put that over my 20 degrees Celsius, but remember, the 20 degrees Celsius have to be in Kelvin. So I'm going to add 273 to that, which gives me 293. I'm going to set that equal to my new pressure, which is 0.667, times V2, because that's what I'm solving for. And I'm going to put that over my negative 10 degrees Celsius, which is my new temperature, but I got to add that to 273. So that's going to give me 263. So I'm going to cross multiply, so it'd be 1.00 times 1.08 times 263 equals 293 times 0.667 times V2. I'm going to divide both sides by 293, and I'm going to divide by 0.667. And what I end up getting for my V2 is 2.42 liters. Notice I have three significant figures because my volume and pressure both have 3 sig figs each. My temperatures, when I add 273 to them, they both have 3 sig figs. Notice my units for volume were in liters, and therefore my new volume is also going to be in liters. So those are the last 3 gas laws that we're going to be looking at. Okay? We have one more that we need to look at, but that is going to relate pressure, volume, number of moles, and temperature. That is your ideal gas law. But these 4 gas laws that you've looked at allow you to compare what happens to variables when you change, for example, pressure, when you change volume, or when you change temperature. Okay, so that's what makes those 4 unique.